Thank you very much. I think most presentations start out with people saying to silence your phone, but I want to say take out your phone if you can, if you have a mobile phone. And when I started looking at rare metals, I looked at it from a geopolitical angle. I was in Japan in 2010 when China, during a territorial dispute, cut off exports of rare earth elements, so the subset of, I don't think I have to go into the periodic table, but a subset of elements which I include in a larger set of rare metals or minor metals. And I had no idea the spread of rare earth elements into a number of applications. And I never realized that how many elements, including rare earth elements, were in this phone here, that we have roughly half the elements known to man in these things to make them work. And when I look at them, I see that I see something so simplistic. But I realized when this thing came out that the products that are going to come after it are so much more advanced, even though they look simpler, and that we've kind of entered a new age, and which I call the rare metal age, because of the preponderance of these elements that are going to increasingly be in all of our products. It's just something strange that I've noticed is that the same toys that we have as adults are also the same toys that children are having. And they're all becoming more advanced and relying on these metals, and will increasingly do so over the future. Now, what I had mentioned is that I had worked in Japan in the Ministry of Economy, Trade, and Industry when China cut off exports to the country. So I had this ringside seat into this geopolitical battle. But to jump a little bit further into my background, I used to work in energy trading, I used to work in finance, and a little while I used to work on federal natural resource programs in Washington, D.C. And so it's all given me a background into what are these resources, what resources are. But I think there's something very unique about these minor metals, these rare metals, that are very different from copper, from oil, from coal. Because one is that they're really produced in small quantities. When we think about copper, it's something that's produced in the millions of tons annually, 17 million tons annually. But when we look at dysprosium or neodymium or germanium, they're produced in the hundreds or thousands of tons annually. So they have a very different supply dynamic. They're often, because they're produced in such small quantities, produced in either one mine or one country. So that gives a country outdo influence in the market, or that one mine or one company outdo influence. They're traded in backroom deals. So a lot of the larger commodities are traded in exchanges. So you know where the price is, you know if you're going to order it, what you're going to get. But these are often traded by people who've been trading these things for decades. And they bring it from one place to another, and secrecy is key because it helps the bottom line of a lot of these traders. One other thing is that this is somewhat true with oil and gas and certain other metals, but very particularly true with minor metals, is that the supply line takes 10 to 15 years to set up. So if you think about it, the products that we're going to invent in the Teslas and all of the products of the future that are going to come out in 2020, 25, or 2030, we're making the resource base now. And the reason why it's so challenging to produce, or it takes such a long time, is that it takes time to raise money. A lot of these materials are byproducts, so that there's often a challenging chemical or heat process to develop to produce the metal needed or the material needed. So there are a lot of complications in terms of producing the material. It's not just like in certain cases gold, where you can just pick up a nugget or pick up a little chunk and the metal is there. As you guys know, it's often a challenging process to turn mineral into a usable material. So you've got these challenges really to develop a robust rare metal base, but at the same time, our products are changing, and the use of rare metals is spreading. What I mean by that is when I look back at the products we used to use, the light bulb, and now it had a tungsten filament, but it was a very simple product. It didn't use many materials. And when we look at our homes 20 years ago, because our products were simpler, you'd find roughly 20 or 25 elements in the houses a generation ago. And now the iPhone uses half the elements known to man. General Electric uses 70 of the first 83 elements on the periodic table. We're seeing this drastic change in resource use. And when you look at the light bulb today, even though it does the same function as this old one, this one here is more akin to a computer than it is to its old light bulb. And it has its similar amount of rare earth or rare metals in it, neodymium, dysprosium, gallium, each performing a specific task. And usually when I talk about the traits of rare metals, I do a couple different experiments, but I'm going to limit them just to one here, because I assume you have all your experiments going in your labs. But one of the interesting metals that I like to talk about is titanium. Now, titanium is produced in a little bit larger quantities than other minor metals, but it has a number of interesting qualities. And one of them I like is shape memory. Do folks know what shape memory is? Shape memory is?
It will return back to its original position when you do something to it.
Yes, yes. So this is, could you explain what this is here?
It's a slinky.
It's a slinky. It's a titanium slinky. So can you separate it out for me? Just all the way. Okay. And then can you put it back together?
No.
Okay. So it makes it a little bit of a challenge if the experiment doesn't work. But if you have a little bit of heat, what you can do is it comes back. So that's the secret, yeah. And then you have to play with it a little bit so you don't burn yourself. But it comes back. So this is useful for things like eyeglasses. So when you step on them, it returns back to its original shape. But the reason why I bring this up is this isn't so useful in your iPhone. But each element has something that's very specific about it. And what it does is it creates challenges to replace one element for another. Oftentimes when people talk about trying to replace an element, they think it's something that's very simple to do. But it's not. And if you think about it, we've been trying to replace sugar from our drinks. And I can look back, and I have a Diet Coke right now, and I can tell you the Diet Coke without sugar doesn't taste like the real thing. And the same things will happen with elements. It's hard to take one material out and put in something else. What you're finding is that you're going to have to change the whole product itself. I mean, imagine trying to take a lithium battery out of here and putting in a 9-volt. It wouldn't work, and you'd have to change the whole thing. And it would be chunkier. And there's a whole bunch of other problems it would have. But kind of jumping back to demand in the future. And we're seeing these increases up because there isn't an ability to substitute certain materials. So you're going to see demand continue to soar for certain specific metals for certain specific applications. The products that we're using now, we're using them far faster than we did in the past. So we're churning through phones, through laptops. We're using them every 2 or 3 years. And in the past, products used to last longer. So not only are we using more specific metals, using more of them in applications, but we're churning through them much faster. So there was a Japanese study that talked about the life cycle of a commodity within its use, and it's over the past generation, it's really jumped down from 10 to 20 years to really just 2 now because of this faster churning through materials. We've also have a challenge in the electronification of our products. The toothbrush, things that weren't electronified are now electronified. So we're seeing more things entering what they say the Internet of Things. In 2010, there were roughly 12.5 billion things connected to the Internet. By 2020, that number will increase 4-fold. And part of that has to do with this emerging middle class globally. In 15 years, we're going to see another 2 billion people enter the middle class. And these people are not only using the resources in ways that we do, they're using them, they're even gravitating more to them. So there's a gentleman I met actually I never met him. I tweeted to him, I Facebook messaged him, I text messaged him. His name is Sessa, and he's based in Jakarta. Sessa makes roughly about $300, $350 a month. He has a tablet, he has an iPhone or smartphone, he has a laptop, he has a game console. He has a number of different he has more of this electronics wizardry than I do. But he makes such little money. But he's addicted to it. He's on social media half his waking hours, he tells me. Within 5 years, he had about 142,000 tweets, which means he's tweeting over 500 times a week and over 70 tweets a day. So he is never putting down his phone. But he does assure me when he's driving his scooter, he doesn't tweet because he drives safely. But when he's driving his car, that's a different story. He may tweet then. My point of bringing him up is there are millions and close to 1 billion of this new generation who's sticking to this high technology. And they're going to demand it. And we have to find ways to develop supply. And I think the challenge isn't, are we going to run out of materials? I try not to look at a peak oil or a peak neodymium. The challenge is a little bit more nuanced. It's ensuring that the right material can meet the right place, go to the right place at the right time, at the right economic and environmental price. And I see that becoming a challenge because we're coming to a time where supply chains take 10 or 15 years to develop, but the technology is advancing far faster. So the smartphone was the product that made it around the world in the fastest time period in the history. So what I mean by that is within 4 years of its invention, 6% of the people in the world owned a smartphone. No product, not the television, not the air conditioner, not the radio, went around the world faster. A few years later, the tablet came out and beat that record. So we're seeing this proliferation of products around the world, which is a wonderful thing because it can enable people to get out of poverty. It opens up a lot of options. But the challenge is when things can spread around the world so quickly, and when green technology is right in the offing, and if we're going to make great strides against climate change, then we're going to have to ensure the resources that are needed for these products are available at the right price. So people often ask me, I spent 3 or 4 years traveling around the world. What are the places, where does this stuff come from? What do these places look like? And hopefully I can show you. That's it? Oh, there we go.
There we go.
Okay. All right, so this is Bangka Island. Do people know where Bangka Island is? It's off the coast of Indonesia. Most of the world's tin comes from this area. I didn't focus much on tin, but there's some other byproduct metals that come from this area that I was focusing on. But this is illegal mining in Bangka. What you see here are these little houses on the water, and they're roughly like 200, 300 feet off, a little further, depending on the area. And you have to take a boat out to them. And the beach itself is beautiful. It's a stunning beach. But these docks, these platforms, are some scary operations. It's loud because you've got these engines. Each one has an engine, and they're powering what is essentially a large vacuum. And what these people do is they go down underneath the surface about 8 feet or so, and they're sucking up sand to bring the sand up. the mineral-rich sand up on the boat. Okay, and they're going down and sucking up the sand, and they're just in essence building ditches underwater, and they're building ditches, some that go several feet deep, and they're vacuuming it up. And if it sounds dangerous to be digging up sand underneath water because you think the sides of a ditch underwater may collapse and trap someone, and who gets stuck down there, and it is dangerous, and many people do die trying to get a lot of these the material out. But when it does come out, it's brought up on the ship where they try and wash away the sand and keep the mineral-rich deposit. So as the sand gets a little bit darker, they get a little bit happier because it's collecting more of the minerals that they need, and that's a sampling of what they showed me. Now, not all mining is coming from illegal areas, but it's more fun to show you guys pictures of illegal areas than it is to show other areas. This is in China. So I talked about mining itself is often the easiest part of getting the materials up. It's the processing that's more challenging. So for rare earth elements, that is the case because they are pretty widely dispersed. The challenge is trying to find the right mix, chemistry balance to ensure that you can get the minerals out to oxides. And you see here what they have are large chambers, and there's a whole material flow just to get each rare earth element out of the mix. This is actually a legal facility in China. And this is a smelting facility in China. So you've got most rare earth elements don't go to metal form, but some do. And this is one of the facilities in China. Again, this is not an illegal facility. It's just not one you would want to work at. So when I was there, my nose started to burn, and my eyes started to tear. And I looked at a scientist who was with me, and I asked him, "Is this supposed to happen? Because it doesn't feel good." And he said, "Yeah, if you're going to breathe in this much fluorine, then it's not going to feel good." And so what he said is the ventilation systems don't look like they work so well. And I don't know if you can see so well, but the ventilation systems don't appear to look like they work. I think the one in my house that sucks out the smell of the chicken when I'm cooking is stronger than these. So you've got gentlemen in there working for many hours, over many days, over many years, facing a number of challenges. One of the things, I'm going to just talk for another 2 minutes. This fascinated me. This is in southern China. The soil is a brittle clay. And one of the fascinating things is that a number of heavy rare earths, dysprosium, terbium, europium, come from this region. And mining in this region is rather easy because it's a very brittle sand. You can see you can carve the space out. You don't even have to dig, you can just carve. So they put this building kind of on the side of a mountain. But the challenge with mining clay, at least the clay that's here, is that although it's easy to mine, it's not very rich in minerals. So you've got 0.2% of the material that needs to be processed. So 99.8% is waste material. And if you're digging out off the sides of mountains, you can't put back 99.8%. So you've got all of this excess material that's got to go somewhere, and it goes in streams, and it goes in a number of places. So while it's really easy to mine, it really causes a heavy environmental toll in this area. And when I was leaving, flying away, you could just see some of the scars that kept going through southern China. So I don't want to take up too much more time talking, but I really just wanted to kind of highlight some of the demand challenges, or the reason why demand, I think, will continue to increase, why supply is a little bit challenged in getting the right material at the right price at the right location. It's something that we'll see more market spikes, price spikes in the future. as a demand rises, but the supply won't necessarily be there right away. And then just highlight some of the stories along the supply chain.